Welcome to today's lectures. We want to look today into neural networks, and the goal is to provide you the core idea what neural networks are and how can we use them to solve certain tasks in the context of image interpretation. So you may have heard that neural networks are today one of the techniques that are extremely popular when interpreting data, especially image data, and that has a reason because those models are very powerful. And we want to dive today into neural networks and get an understanding what very basic neural networks are. There will be a second part to that lecture where we dive a little bit more into the details, but today we want to start with understanding what neural networks are and what we can do with them. So consider we have an image classification problem. That means we have an input to our classifier and we want to generate a certain outcome. For example, we want to tell what we actually see in an image. So if we, for example, have an image of a cat, so if this is our input to our classification system or a classifier, then the answer to that input should be cat. So we want to build a system where we can put an image like this and it tells us that's a cat. So this is a rather advanced task, and for the purpose of this lecture, we want to look into a slightly simpler task, and this is the recognition of handwritten digits. And so this is a handwritten digit, digitized, and this should represent a 5. So we want to build a system where you can give in images of that form of individual digits, and it should tell you that's a 5, or that's a 2, or that's a 7, that's a 9, that's a 0. So that's the task that we actually want to solve. And we will look into this task of handwritten digit recognition here as one of the examples that will pop up multiple times in this lecture. The reason for this is that it's fairly easy to understand. It's complex enough to let us understand that it's not a trivial task, but on the other hand, not as complex as, let's say, general image classification task like the one we have shown over here. You can use neural networks also to for a large number of other tasks. Also, some approach which is very popular is semantic segmentation, or a problem which is fairly relevant, where you basically don't want to assign a single label to a whole image, but you want to provide a label for each pixel. So for example, you have this scene, this is a view of a car, and you want to label every pixel in that image that's taken from the driver's seat of a car and annotate what kind of object that is that has been pictured over there. So you basically can assign a color to different classes. So in this example, for example, blue would mean that's a car, this pink means it's a sidewalk, this brighter color here is a road, these are the yellow ones are street signs or traffic lights. And you can also maybe want to label buildings as different objects. So the task of assigning an individual label for every pixel is something that we refer to as semantic segmentation. It's also a task that often pops up when we want to interpret image data. For now, or for today, we want to keep it a bit more simplistic. So we just want to look to this task over here of image classification. So we give in, for example, handwritten digit, and it should output. That's a 5, that's a 3, that's a 1, and not assigning a label for each pixel in an image. And for that, we want to use neural networks, which is one of many machine learning techniques out there. And it's a technique which actually exists since quite a while, since the 50s, 60s. The first idea of those artificial neurons came up and ideas have been discussed. Then more theoretical work has been done in the 1990s, and around 2000, at the beginning of 2000, there was an increased interest in neural networks, and then there have been certain developments in the context of neural networks which were able to solve certain tasks really well, especially convolutional neural networks for image interpretation tasks, and this has made these neural networks, especially deep learning techniques, very, very popular. But it's a frequently used technique for things such as classification, semantic segmentation, instance segmentation, panoptic segmentation, all different various of interpretation tasks of images. Not necessarily only images, we can also apply that to laser range scans or any other type of signal that we are recording with images. But we want to look here today into image classification because it's actually fairly easy to grasp and to see what's actually going on. Okay, so let's start with our first part, the basics of neural networks. We want to understand what a neural network consists of, what are key elements of this neural network, what are the parameters of a network, how do we feed an image into a network, how do we get an output class out. These are things that we want to discuss here in this first part. So first thing, let's look into the two individual words, neural and network. So what's neural, or what's a neuron, and what is a network? So a neuron is one of the fundamental units in our brain. We can see this as a kind of basic or elementary computation unit, so that can perform simple tasks. Those networks can typically be activated through an input, so they have an input, then some computations happen, and they trigger so-called activation or an output. And a network is basically connected elements or connected entities. So a neural network basically consists of several neurons that are somehow connected. So a neural network is a connection of neurons or elementary computing unit, and they can kind of exchange information. So they get information in, maybe from our sensor, and they can process this information by doing basic computations and forwarding certain signals to other neurons, to this network of neurons, until we reach a certain output neuron that may then generate an action or an output. And so we have connected neurons, basic computation units, which is part what the neural networks are about. Let's look a little bit into neurons. So neurons were at least inspired by biological neurons, so the fundamental units of our brain, and what those neurons in our body do. What they do is they basically receive a signal. This can be data from a sensor like our eyes or touch sensors or similar things that tell us something, or is a trigger from the external world, or maybe from other neurons. And every neuron receives this information, so there's an input channel, so to say. Then what those neurons do, they kind of transform this information or relay this information, so they can take information and forward information, or can combine information from multiple input sources, and then can forward that out and send this output signal to other neurons, or to our muscles executing certain motor commands like moving our hand, waving. These are things which are triggered through neurons being involved in this process. And so this is kind of the biological neuron. And we can see if we can kind of replicate behavior in so-called artificial neurons. This is not an exact one-to-one mapping, but let's say it's a concept which is inspired by those biological neurons. So the artificial neurons, these are the neurons that we build in our computer through small programs, for example. They also have inputs. They kind of receive an input signal. Can be multiple input signals, or typically are multiple input signals. And then they kind of transform this information, so they do some basic computations with it, and then create, based on those inputs, an output. Okay, so as a result, the neuron receives input, or so-called activations, which is basically the signal that comes from another neuron. And this input either comes from, as I said, a sensor or neurons, and then it kind of combines the information it receives from multiple input sources, or then transforms this information potentially and generates an output or a so-called activation. So the neuron gets activated or is not active. And so that's actually something which is very similar to a function, if you think about it. So a function takes an input, potentially multidimensional input, and does some computation and generates an output, potentially multidimensional, in this case, typically a one-dimensional output. So we can treat our neurons as functions, and that's a key insight. A neuron is basically a function which takes an n-dimensional input vector, then does something with this n-dimensional input vector, and generates, in our example here, a 1D output. So n-dimensional input, some magic happens in here, and we generate a 1D output. And this output is typically called an activation. This basically tells us if this neuron is active or not. So you can see this, either it has a value, for example, of 0, then it's not active, or it has a value of 1, then it's active. That would be a binary function. But we can, for now, simply see as kind of this neuron stores a certain value, and this value is somehow generated through a mathematical operation. And that's kind of the basic neuron that we are using. We will dive a little bit into the details how this function f of x of that neuron actually looks like. But for now, we say it's an input, it does some computations, and generates then an output or an activation. And that's the function of a single neuron. Okay, so after we have clarified or briefly introduced what an individual neuron is, we now need to look into the network idea, so the neural network. So neural network is a connected set of those neurons. So we have here all those circles sort of represent neurons, and there is some form of connection. So the different neurons are linked with each other. And so it's kind of, you can see this as a graph or as a network which can be used to propagate information or electric signals through this network. And there are different neurons involved and they are connected differently. So some neurons are connected with each other, so this neuron and this neuron are connected with each other through this line, but this neuron and this neuron, they are not, at least not directly connected with each other. So some neurons are connected, some are not connected. But the important thing is just a connection of neurons, and the connections represent a possible data flow. So information that can be passed from one neuron to another neuron. You can see as a neuron can have some inputs, like this neuron over here is 1, 2, 3, 4 inputs, and it generates an output or an activation which is then stored in this neuron, and this can be passed, the same information can be passed on to other neurons. So the edges kind of represent the input-output connections or the data flow in this network. And we look into types of networks where we have something what we call an input, which is typically here shown on the left-hand side, and an output, and something in the middle. So we can see this as an input layer, an output layer on the other side, and some computations which happen in this network in between. It's typically always shown on the left is my input, on the right is my output, and I have some computations or so-called hidden layers in between. So if we now want to connect this network for example, an image interpretation task, that would mean we somehow have a camera which records data, and this camera is in some way linked to those neurons over here. And then these neurons do some computation, some magic happens in here, and then an output is generated. This can be a label saying, okay, what is the camera seeing? Or it can also be a control command. So here in this example, I put in a small UAV, and maybe this neural network controls the UAV based on what it sees. For example, stabilizing the UAV or moving the UAV towards the target location. So it doesn't have to be just an output information in the sense this is a cat or this is a handwritten digit. This can also be a command that executes something. And the neural network itself is, in this case, agnostic to it. It doesn't really care what it outputs. And of course, the network needs to be designed in a certain way to do a specific task. But we can see this input layer here is getting our sensor data or any other type of input data that we have, so the input to the network, and it generates some type of output. So that means we can see the whole neural network itself again as a function. So not only the individual neuron, also the overall network can be seen as a function. So in this case, we have a 4-dimensional input. We have 4 neurons in our input layer over here. Then we have some computations which happen in this area over here. And then in this case, we have a 4-dimensional output because we have, again, 4 neurons in our output network. So the number 4 here and 4 over there doesn't have to be the same. This is just accidentally the case here. So the input layer and output layer have, in this example, the same number of neurons, but that's kind of absolutely coincident. That doesn't have to be that. It could also be 100 over here and just 2 over there. Just depends on what the input to the function is and what the output of the function is that I want to compute. And typically we have some hidden layers in here. So hidden layers, this means that they are not connected to the outside world, so neither to a sensor nor to an actuator. And those neurons in here and those connections, these edges, they perform the actual computations. So what we have is we have the input layer, hidden layers, one or more hidden layers, and my output layer. And the network which is shown here is a special form of layer, so-called multi-layer perceptron. So perceptron, an individual perceptron is also kind of a neuron, something that perceives something, generates an activation, and we have multiple layers of this. And also in this MLPs, the data flows always from one side to the other side. So kind kind of here from the input layer through the hidden layers into the output layer, and the information is always forwarded in one direction, so there are basically no loops in this network. And these are kind of the very basic networks which exist since quite a while, also often called kind of the vanilla neural network. So one of the simplest, or a fairly simple neural network, but one which we can use to solve certain tasks actually quite well. So what we have this function which takes an n-dimensional input and maps it to an m-dimensional output, and this is kind of what our neural network does through the X. So the input data forms our input layer, then we have the hidden layers, and of course the connections between input and output, which then generates some computations, leading finally to the output layer, which is my output signal. And so the question is now, how does this function fnn, so f for neural network, f neural network, actually looks like, and how does it perform the computations to turn our input signal into a desired output signal over here. And it should be noted that there are different types of neural networks, and this is just a kind of a small subset of neurons which are out there. So there's a simple perceptron, it's basically a simple single neuron. There are these MLPs, multi-layer perceptron, what we talked about. They are autoencoders, convolutional neural networks, recurrent neural networks, and a large set of other networks which are out there. But we want to focus today only on MLPs. So we are not diving into these other types of networks. Just to give you an idea what the difference between those networks is, there's a nice kind of overview of different kind of types of neural networks which are out there. And you can see there are different networks like feed-forward networks. So the MLP is a feed-forward network that we're using here. Recurrent neural network, long-term, short-term memory networks, GANs, and a large number of different networks. And you can see they have a different structure. And you can also see those, the neurons over here are differently color-coded or different symbols. And there's a legend here, you don't need to go into the details, but it means that there are different types of neurons, so neurons which have a certain functionality. They're not always equal, and certain neurons can do certain things and others can't do those things. And there's a large set, we go on, and one of the very popular neural networks for the image interpretation task are these convolutional neural networks, like one of those networks which is shown over here. We start with your input layer, perform kind of convolutions, and then have a fully connected layer. Then this gets kind of more narrow and narrow, and then my output layer over here. But again, that's something for further lectures if you want to go deeper. We are going here looking into the multi-layer perceptron, or the MLP, which again is one of the basic vanilla neural networks. And again, we can see, as I said before, this MLP again is a function which takes an input X, which is stored in the input layer, does some computations, and generates me an output. And so the input vector X, every individual dimension of my input vector X is put into each neuron, into the individual neurons in my input layer. So if I have a 100-dimensional input, that means I need to have 100 neurons in my input layer. And the same for the output layer. If I have 20 neurons in my output layer, this gives me 20 different values over here, and they form my output Y. So we need to explain how the X actually looks like if it comes from my sensor data, and what Y actually means in order to understand what we can do with such an MLP. But the important thing is kind of the individual dimensions of this vector X and the individual dimensions of this vector Y, they actually form the values in the input and are the values of the output layer. Okay, let's say we want to start with the task of image classification. We go back to our cat example. So we now have a cat image, and we want to kind of feed that cat image into the neural network. So we want to feed this into a neural network, and then some magic computations happen in here, and the output should be cat. So that's kind of what we want. So X would be my input image. The neural network is my function which performs this classification, and Y should be the output label. So I have an input image, it's X, my function that maps images to semantic labels, or to words, so to say, and this is my label cat, for example. And what I now want to do is I want to explain you how we can actually take the input image and turn it into the hidden layer of the neural network, into the input layer of the neural network, and how we can extract what the network actually thinks it did with this output layer, leading to something which we then call cat, for example. So let's start with the input and try to understand how the input of this neural network actually looks like. So we have our image, and our image consists of individual pixels. And for now, let's assume that's a grayscale image. That means for every pixel, we have a grayscale value, a value between 0 and 255, for example. So this image consists of pixels, right? So you can just kind of an illustration here. There's a light gray pixel, even lighter, darker gray, dark gray, black pixel, white pixel, gray pixel, and so on and so forth. So these are the individual pixels encoding here the floor of that cat. And this is the information stored in the individual pixels. And every pixel has an intensity value, a value between 0 and 255, or maybe normalized from 0 to 1. So every pixel is an intensity value. So we can take those pixels and kind of treat those pixels as individual dimensions of a large vector, right? So we can simply enumerate our pixels and say, okay, that is kind of pixel number 1, 0, pixel number 1, pixel number 2, pixel number 3, and so on and so forth until pixel number n. And so we have n, or in this case, n plus 1 different intensity values. And we can basically, what we can do is we can actually arrange them in a vector, right? So we can arrange them in a vector from x0 to xn. So we have n plus 1 intensity measurements that we have, and we arrange them into an n plus 1 dimensional vector. So this means nothing else as taking this intensity value, copying it to the first location, first dimension, this intensity value to the second dimension, and so on and so forth until the last value, the dark pixel, is put here into the last dimension of this vector. So we have a n plus 1 dimensional vector which consists of the different intensity values, and these are exactly the intensity values, just copied the pixels out of our image. And those values here, those values between either 0 to 255 or 0 to 1, or however we encode it, actually forms directly the first layer of our neural network. So we are taking the intensity values and are writing those intensity values into the input layer of our neural network. So this could be, for example, a value of 100, this may be 200, this may be 0, and we just write 100, 200, 0 into this input layer. Into those, we fill those neurons. And that's kind of the input, how we feed the whole image into the neural network. And if you think about this, it's actually fairly simple what we're doing. We are just taking this two-dimensional image structure, turning it into a very long one-dimensional vector and saying, okay, this one-dimensional vector is just the input to our network. And every neuron gets exactly one intensity value assigned to it. Okay, so then the next thing is, how do we generate that output? So how do we bring the network or enable the network that it has the ability to say, that's a cat? And for that, what we typically do, we don't ask the network to spell out cat, so 3 characters C, A, and T. What we're doing, we basically have a certain set of classes. And one class may correspond to a cat, the other one may correspond to a dog, to a human, to a bike, to a car, whatever objects we want to feed to our network and let network estimate what it is. So we can basically see this as an indicator vector. So if you look into the first element of the output neuron here, it basically says, is this a cat? So if this is a cat, this should have a high value, and if it's not a cat, it should have a low value. Or is it a dog? If it's a dog, cat should have a low value, and dog should have a high value, or should be 1 and 0. Or if it's a human, or if it's something else. So you can basically switch on a switch saying, hey, that's a dog, that's a human, that's a cat. And basically we have switches. So we can see these outputs here as switches. So that we can see the output as an indicator vector where it says, okay, here cat is switched on and all other classes are switched off. Okay? So that's the output. If you get 1, 0, 0, 0, it means it's a cat. If you get 0, 1, 0, 0, 0, it means it's a dog. If you get 0, 0, 1, 0, 0, 0, it means it's a human. So that's the way how the network communicates with us what it thinks it sees on that image. So those output values of my neural network are directly this indicator vector and should contain zeros and ones. But zeros and ones are typically not sufficient only in the perfect world, because often we may never be certain what it actually is. And even if we have functions of which outputs a value, maybe say, maybe it's a cat, but maybe it's a dog, but I'm sure it's not a human. That's an example. So we should enable the network to tell us something out, maybe an indicator vector which doesn't consist of zeros and ones, but saying larger values has a higher likelihood, is more likely that the object itself corresponds to that, to that type of object we are considering here. Okay, so that's what we want to do in here. So that means we get a vector out which consists of values, for example, between 0 and 1, but could also be larger value. It just means the larger the value in this vector, the more likely it's actually this type of object. So instead of having a binary 0, 1 vector over here, we now have continuous variable saying here, the higher it is, so the higher the indication, the higher the likelihood that the object we see actually corresponds to this label. Okay, so now the network, we know what the input and the output to that network is. So the input was our image, our x vector. It's just the vector n plus one dimensional vector stacked with all the intensity measurements. Then again, some magic happens in here, and the output is this indicator vector or vector full of likelihoods that tell us what's a possible label that we see in that image. The higher the value, the larger or the higher the likelihood that it's a cat. Let's, for the moment, assume something between 0 and 1. May say 1 is a cat and 0 means that that's not the object or not the cat that I'm looking into. And basically what we then have as humans, we basically have a table which dimension of this vector y corresponds to which label that we as a human give to that image. And that gives us the word cat. So basically the largest value in this vector, we say that's a cat, for example. But we as humans provide this label cat because we need to provide with a system with pairs of those images and labels, and the system just says these are different labels, and we just basically need to write down on a piece of paper somewhere that the first dimension, for example, refers to a cat, the second dimension refers to a dog, and so on and so forth. And that's kind of how that network should work. What's the input and output to those networks? Okay, so now what we want to do is we want to understand what happens here in between, right? So what happens between this input layer and this output layer? And for that, we look into our MLP, and we will just want to look for now into a single neuron. So we ignore that is a whole network, and we just look into one single neuron. So we disable everything, we just have this neuron, and it has some incoming connections. Some inputs from, for example, the input layer. For now we can assume it's the input layer, but the same holds later on for any other layer in our network. And we want to understand what this perceptron or single neuron does, how it operates, taking those inputs and turning them into a known activation. So what we have here are our inputs. These are kind of the neurons of the previous layer, either the input layer or one of the hidden layers in there. And all the neurons are linked to this individual neuron over here, which we want to look into, and it generates an output. So it generates a computation, a value, so-called activation. There what's called, we use the letter A over here, or it's my output activation, so the output of that network. And it does so using some function. So we can say, okay, my output A is a function that takes as input all the activations from the previous level, all my input values. So again, if this is the input layer of my network, this would be the different intensity values. If I'm somewhere in my hidden layers, deeper in the hidden layers, this would be the activations from the previous layer that I have. Now the question is now, how does this function actually look like? How do we compute this neuron over here? So what do we do with this neuron? And again, we want to now specify a function and provide a function which we can use for performing this computation, which only uses the input activation from the previous layer and generates the output activation for the next layer. And it does so by taking weights into account, weights for these connections. So a weight for the connection of a connection basically says how strong should the impact of that neuron be. So if this is a connection on edge which is a very high weight, that means this activation will influence the result of this neuron in a strong way. If I have a weight which is 0, for example, it means this has 0 influence. So we have a set of weights, so we have n+1 different weights which are assigned to the individual edges connecting the current neuron with the previous layer with its inputs. And these can be values, can be positive, they can also be negative, so that a neuron can make a negative contribution to a neuron. And this function f somehow needs to combine those weights and those activations from the previous layer and combines them into a new value, into a new activation. And for that, it uses different things. It uses the input activations, just said before, the weights that we just introduced before. Then we have a bias, or so-called activation bias, which tells us how easy it is to kind of generate an activation here in that network. So basically, this value tells us how easily will that neuron be switched on or switched off. And then it has a so-called activation function, and this is, as the name says, is this neuron active or inactive? And then it creates an output activation, which is basically the output of this activation function. So the input of this activation function will somehow combine the input activations, the weights, and the bias. And it does so by simply summing up the individual activations from the previous layer multiplied with the weights of the edges. So basically, it's a weighted sum of the input activations. So weight 0 times activation 0, weight 1 times activation 1, and so on and so forth until weight n activation n. So it's just a weighted sum of the input activations. And then plus it adds a constant, this bias activation for that network, and squeezes them through a so-called activation function. So what the system does, it collects the input activations, multiplies them with the weights, adds them up, and then adds a bias and puts the result through our activation function. And if we look to this function, we can actually see that some parts of this function, not the whole function, look actually very similar to a convolution. So remember when we looked into local operators for image interpretation tasks, then we used convolutions in order to define those outputs. And you can see this basically, what this weighted sum does, it basically corresponds to a kernel represented with the weights, and the input activations, which in the example of local operators corresponds to the intensity values of the original image, which is actually the case for the input layer. And then it adds some offset to it and squeeze it through a function, though this is something that we haven't done in the convolution. So this part is actually very similar to the convolutions, except that we don't slide that kernel on, don't slide it yet over our image. So it's basically an operator which takes all the input pixels and the weight into account, computes a weighted sum, and then does a little bit extra. But there's a direct link, or quite some similarity, let's call it that way, between these computations here and what we used in order to define local operators. The only thing which additionally comes to this is the activation function and the bias function, and additionally, kind of in the convolutions, we basically slit that over the whole image. But remember, we are using it here only to compute one single output value, so kind of one single pixel value. So we were doing this sliding of the kernel over the input image to generate the individual pixels of the output image. Here we basically just created, so to say, just one single output image. Therefore, this sliding operation, as I called it before, that was not really correct because we're just using it to compute one pixel output value, and then there's also no sliding in there. So what happens here is actually one step of this convolution and then adding a bias and an activation function additionally to that. How does an activation function look like? So biological neurons are typically active or inactive. And we can represent this, for example, with a step function saying whenever we have small values, then this is actually not active. And whenever we have, for example, positive values here, our neuron would be activated. So this would be a single step function that I can do. And if we do this, then basically the bias, given that it's here the weighted sum of input intensities, input activations and weights, plus the bias basically tells us where that step happens. So how easy it is to switch on the neuron. If you kind of shift the step further in this direction, it will be harder to kind of switch on that neuron or activate that neuron. If I move it to the other side, that's actually smaller. So we can see this by saying, yeah, through this function, and basically the weighted sum, if it is smaller or equal than the negative bias, I get a value of 0. So I have no activation, and otherwise I have the activation of 1. And this is kind of an analogy to, for example, how I could interpret a biological neuron, let's say that way. The problem with step functions is whenever we do optimizations later on or trying to find parameters, step functions are always hard to optimize because there's basically no gradient here, no gradient over here, and an infinite gradient over there. There's always something which is kind of suboptimal in terms of optimization problems, or often suboptimal. Therefore, we may prefer a smooth function which smoothly activates from 0 to 1 and is not this type of an extreme step function. And one way to do this is a sigmoid function, or also called a logistic function. So this is a function which squeezes basically all the possible values into the range of 0 to 1 and has a smooth transition from 0 up to 1, which is a smoother function which may have some advantages in the underlying optimizations. So it's a smooth function. All the output values lie between 0 and 1, and I can feed in values from -infinity to infinity, and they will generate the output activation 0 and 1. And that's kind of a commonly used functions in neural networks, especially into kind of simpler or smaller neural networks. You may want to go to different activation functions in larger networks. Also, different layers in your network can have different activation functions depending what you exactly want to model. But this already goes a little bit deeper into the different types of neural networks that we have. For now, we will just assume we have for all our nodes one of those activation functions in here. And again, this can be the sigmoid function, can be very easily described with this form. I want to mention another activation function which is frequently used, which is called the Relu function, or Relu. It's basically maps everything to 0 for values that are smaller than 0, and then takes the identity function for all functions which are larger than 0. And this has some advantages, especially for very deep networks, where you have a lot of layers which are stacked to each other. And so this is a function that you also frequently find in those kind of larger networks that we have. And again, in this case, we basically have no activation here on that side. We have an activation over here, but the larger the input value is, kind of the stronger the activation of that neuron. And so the stronger the effect of that neuron will be on the subsequent layers which follow that. And again, as before, B is our bias, which basically tells us where I'm starting to go from the constant function, constant 0, to the identity function. There's also, again, a variant of this, is a leaky Relu, where this function is not 0, but again, it's a small slope, but here the slope is much, much smaller than over here, which can have some advantages with respect to the gradients in this area of the network. So to sum up, there are a large number of different activation functions. I just looked into sigmoid, Relu, and the step function over here, but there's a large number of other step functions, and Relu is a commonly used choice for setting up these activation functions. And again, there are some examples how those functions look like, but you typically see these always functions which go from small values to large values. Often they are kind of limited to 0 or 1, or from a small value maybe to larger increasing values or identity values, but they always have kind of this shape that they are kind of small on the left and then increase towards the right. And this is always the equation for this corresponding activation function. And for the optimization part, and when I want to determine the parameters of all those neurons, then the gradient will actually, the first derivative will actually play a role. But this is something that we don't need in this lecture today, but in follow-up lectures. Okay, so the function behind a neuron that sits behind neurons is now something that we have actually specified. So it is this either sigmoid or Relu or a similar function. It takes the weighted sum of all input activation, adds the bias, squeeze it through this activation function, and that's my output. So a fairly simple function, if we are honest. And so the question is, how can we actually, with this set of fairly simple functions, generate some potentially intelligent or intelligently looking behavior? Let's call it like this. And this can actually be generated by using a large set of those functions which are combined. And remember, that is just the function which sits in one single neuron. What happens in our neural network that we have a lot of those neurons, and they are all connected with each other. So typically, all elements from one layer are connected with all elements of the next layer. So basically, we have full connection between all the individual layers, but typically layer whatever 3 is not connected to layer 1. So only from layer to layer. And that means there are potentially a very large set of neurons, and that also means there are a lot of those values. There are a lot of those weights and biases that I need to specify. Again, all those edges here correspond to one weight, and all the circles here correspond to one bias. And there are actually a lot of those edges. There's kind of the number of edges in one layer times the number of edges in the previous layer. So there are a lot of those weights that we need to take into account. And at some point in time, we need to also determine the parameters, so which weight it actually takes. And this is where this becomes a high-dimensional state estimation problem later on. Okay, so what I first want to use, if we have all those different weights, and now we have another index added in here, so always this index here on top tells us in which layer we are in. So this is the input layer 0, the first layer, and then we have weights with 2 indices, one which neuron it comes from and to which neuron it's actually connecting to. And then the function that we have in here looks again a little bit more complicated, but it's not more complicated, it just has more indices to reference to the individual layers. But what we actually have in here is something that we have input elements which contribute to an output element, and for that there are a lot of always kind of pairs of those edges which are associated with weights taken into account. So that's actually something that we can arrange in a matrix form. And then, as we'll see, it gets much more compact to write things down. What we can see is we can arrange those weights in a matrix, and therefore we have written these 2 indices here, so that directly ends up in a matrix. This vector A is a set of all activations of the first layer. And these are all the activations of the layer 0, so the input layer. And these are all the biases of the neurons in the first layer. So what we have is this single value gets into a vector. This single output value gets into a vector. We stack all those input activations as one vector, and then we have the matrix consisting of all the weights. So it stores all the weights in here. And if we arrange it in this form, then we can actually write this as a matrix vector product plus another vector, and then every individual dimension squeezed through our activation function. So basically it means for every individual dimension of this vector, we are actually executing this activation function. So this means the layer number 1 can actually be computed from the layer number 0. So this is our input. We multiply this input vector with this weight matrix, add the biases, squeeze it through our activation function, which gives us then our second vector. And so we can actually write this down in a rather complex form, writing this as a weight matrix, our activation vector, our bias vector, our kind of dimension-wise activation function, and which gives us our new layer. So in this very complex compressed matrix form, I can actually put in all those weights in a rather elegant way. So that all the computation that I need to do in order to compute how the activations in one layer look like given the activation of the previous layer can be executed with basically a few lines of linear algebra code, plus this activation function, depending how it looks like. Okay, so, and then we can do this actually layer by layer. So we start here from our input layer, we fill our input layer with our pixel intensity values, and then we compute the first layer, or the first hidden layer, based on those values. And then the second hidden layer based on the first hidden layer, and then the output layer based on the last hidden layer. So again, we always do the same computations. So this is our input that we feed in over here. We multiplied with our weight matrix. So this is a weight matrix which corresponds to those weights over here. So of the leading to the from the input layer to the first set of neurons, and the biases, which will give me the output activations. So these are the output activations. And then I repeat this process over and over again until the last layer, where this is here the last layer, last hidden layer that I put in, multiplied with the corresponding weight matrix, which corresponds to those weights over here, add the bias, and obtain my output activations. And this is, in this case, my output layer, so the result of my neural network, or the output that my neural network actually generates. So in sum, if you write this down, we have our input layer, which is a vector of activations. These are just our input pixels. Then we compute this computation for layer number 1. And then we take the result of this output and put it to the input of layer number 2. And we compute this through all hidden layers until we reach our output layer, which is our layer k, do the same computation again, and have our output. So evaluating this neural network is actually nothing else than linear algebra, or not much more than just doing a few matrix vector multiplications, adding a bias, and squeezing it through this activation function. But if you think about the Relu as the activation function, it's basically an identity for all values larger than 0, and whatever is smaller than 0, we just set it to 0. So it's a very simple operation. So that with the library, which performs well or very efficiently performs this matrix operations, or even using hardware acceleration, you can perform these potentially large number of computations in a fairly efficient way. And therefore, it makes sense to actually write these things down as matrices and vectors. So I already mentioned before, here we are using a so-called feed-forward network. That means our input goes to the input layer, and this goes from one hidden layer to the next hidden layer to the next hidden layer until we reach our output layer. So the flow of data is always from the left to the right here in this example. And there are no loops in this process. These are kind of so-called feed-forward networks, and the MLPs are such a feed-forward network. Just be mentioned that there are other variants like recurrent neural networks where you can actually feed this information backwards, or you have loops in here, but that's something that we are not considering here for that moment. Here we are just assuming we have those networks without any loops. And with this, I want to go to a concrete example, the example of handwritten digit recognition, and dive a little bit more into the details, so to illustrate what those individual parameters actually do. So we have handwritten digits like these kind of scanned characters over here, and we assume we have an approach which separates them into individual digits. So we have small individual image which look like this. In this case, this is a 28 by 28 pixel image, and we want to assign this to a label. So this is the character number 5, and we want to perform this task of putting in any of those individual digits and providing the corresponding label, which of the 10 possible digits it actually is. And our assumption is here we have all the characters isolated, and they all come in a 28 by 28 pixel image. So our database, but these are examples of 0s, 1s, 2s, 3s until 9s, and this is the data that we actually want to process. So at that point in time, we're not talking how we actually learn what the network should do. So we are not saying, okay, this is a training set which I use to train my neural network. That's something that we do in the second part of that course. Here, we assume we have those weights and biases given, and what we want to do is we want to classify this type of data. Okay, so I said all those images are scaled to 28 by 28 pixel images. That means we have an input layer which has a dimensionality of 28 times 28, which is 784. This performs our input layer. And then we have an output layer which consists of 10 outputs, basically saying, is this a 0, is this a 1, is this a 2, is this a 3, and so on and so forth, until is this a 9. So there are 10 possible outcomes, and these are given by this 10-dimensional output, basically being an indicator vector where the activation, the largest activation basically tells us, yes, that's actually the output that I want to have. So as the input to this network, we have this 784 dimensional input resulting from the 28 by 28 intensity values, and we want as an output a 10-dimensional output vector. So in this case, in this example, this is 0, 1, 2, 3, 4, 5 is active, and all others are 0. So this would be the perfect outcome for putting in this 5. Okay, so the question is now, what actually happens in those hidden layers or in those layers? How do those layers actually look like? How do they actually operate? What are those weights doing? And again, I don't want to talk here about how we actually obtain those weights or how we obtain those biases. I just want to illustrate, given those biases, what they actually do. So the question is, what happens in the individual layers? And I want to now go through those different layers of our network. And again, in this network, we just have 2 hidden layers. The first layer is 128 neurons, and the second one has 64 neurons. So the numbers are, let's say, a little bit arbitrary. This is kind of the structure, and basically tells us something about patterns that the system recognizes and how many different patterns the system can try to find later on in this input data. So it doesn't really matter if it's 128 or 150, but if you shrink it down to 2, this would be too little, and 10,000 are too large. So, but the actual number, the precise number, is something which is a bit arbitrary, and we just provided them here. It's at least hard to determine how large exactly those, the number of neurons here actually should be. Okay, so what happens in those layers? Let's inspect what those layers are doing. So we are here in our first hidden layer, which are our 128 different neurons, and they get an input from all 784 inputs. So this means this weight matrix here is a 784 by 128 different weights are stored in here. So this means for a single neuron, I'm not just looking to this single neuron over here, I'm ignoring all the rest. So those guys here I'm ignoring now, I'm just want to look into this neuron over here. This neuron has 784 input activations, basically all neurons on the previous layer, and thus the same number of weights, because we need to weight every pixel intensity. So every pixel intensity is multiplied with a weight and is the input to this neuron over here. And of course, the other neurons do that in a very similar way. Okay, so just for illustration purposes, let's go back and say, okay, we have this vector over here, and kind of 784 pixel intensities. Let's kind of rearrange them into an image, not into a vector, just for illustration purposes. We can do the same with those weights, which is exactly the same number. So we can put the weights into exactly the same type of image. And so just for the illustration purposes, let's treat those activations and weights as images. In the first layer where we are right now, those activations are actually pixel intensities, but in layers later on, they are not necessarily corresponding to our individual pixel intensities. And the weights are just external parameters of the network, which we don't look into how we obtain them right now. We just assume that is given, but we kind of rearrange this 784 dimensional vector, weight vector, also into a 28 by 28 image. And then we actually get the following. So these are our pixel intensities, so our pixel values actually in A0 from our input layer. And then we have our weight layer. This is just one single example, just an illustration how such a weight layer could look like. So there are some pixels over here, the green ones, which say have a positive value. Let's assume positive 1. And there are some values, which are illustrated in red in here, which are actually negative, or sorry, one is negative, the other one is positive. And all the values in between, which are not encoded in color here, take the value of 0. And depending on if it is -1 or a +1, basically depends if black is 0 and or white is a 1 or 255. So it depends on how you encode your image. So what it basically does, it says over here in this white area, it's basically weight is 0. So it means this intensity activations are not interested at all. They are all put to 0. The only values I'm interested in are the are the green ones and the red ones over here, because the green ones are those for which I get punished if they are activated, and the red ones I get rewarded when they're activated. So if in this example I say white means high values and black means 0, then if I kind of make now the overlay between the pixel values and the weights, basically I'm counting the black pixels in the green areas and they give a negative reward. Black means 0 value, so if it's black, that's good. It doesn't punish the network. And the plus ones over here are those which actually take a high value. These are those white pixels. So I get a positive reward, a positive weight, a positive reward in the activation of the neuron for those values under this red stripes over here. So what basically means, whenever we have white pixels under the red area, that's good. And when I have black pixels under the green area, that's good. And the rest doesn't simply matter. So the more the input image corresponds to kind of this line over here, so a short line. So if this part over here of the image looks like a line, this weight will actually say, that's good. I give a maximum reward. I don't care what's anywhere else, but as soon as this kind of looks like a line, I'm happy. I'm actually triggering a high activation of the highest possible value that I can actually generate. So what happens in those layers is basically the individual weights that corresponds to every individual neuron look like this, and they basically tell us which input intensities should be there and which should not be there, and for which they don't care. Basically, those zeros could also mean we're actually dropping those edges over here. That's equivalent. They don't matter at all. So the individual weight images of the neurons are actually small pattern recognition systems. So they try to recognize a certain pattern and give a high value when they find that pattern and a low value if they don't find that pattern. Okay? So that's kind of really important now to understand that it's basically a system which finds patterns, and the weights define how the pattern should look like so that the neuron gets activated or doesn't get activated. So the weights basically give you the shape of that pattern, and the bias basically tells me how strong should that pattern be visible. So how strong should be the difference between the white and the black pixels, for example. So how strong this effect should be, or is it sufficient that only half of the pattern is actually satisfied and the rest may not be satisfied. This is kind of what the bias actually tells us. And again, there is a direct link through the convolutions that we have used when we defined image operators. So we can actually see this weight matrix and the input image as a global operator, which generates an output just for a single pixel, taking the whole input image into account. And the weight matrix basically tells you in which way you want to combine the input intensity values to define the output value over here. So this weight matrix does not yet kind of slide over the image to say, I just want to find this pattern. I don't care where the pattern appears. This is not the case here. Here it says we want to have that pattern, and that pattern should actually be located over here. But that's something that we can later do with convolutional neural networks, that we actually get those real convolutions into the game. So how do the weights and biases actually look like? The weights and biases, and this is kind of the key insight here, are look for patterns, or the weights define the patterns, and the bias, how strong that pattern signal should be. So how well the image must match that pattern. And then if the pattern is found, the neuron is basically switched on. So you can see the neuron as an indicator lamp saying, yes, this pattern appears. Yes, this pattern appears. No, this pattern doesn't appear. This not as well, this not as well. The next one appears again. So it's basically indicator lights saying you this pattern is there or this pattern is not there. So in this first layer, for example, these may be patterns that we are actually looking for, individual small patterns. The question is now, what happens in the next layer? What happens in the second layer? And actually, the structure is exactly the same. The second layer can be seen as picking up now not intensity values that I found before, but patterns that I found before. And what it now does, it basically combines those patterns. For example, if the neuron which says this pattern is there, this pattern is there, and this pattern is there are all switched on at the same point in time, I know, okay, Here's something which looks like this. There's something which looks like this, and there's something which looks like this. So you can see it kind of turns like into a circle. So in the next layer, the neuron basically tells me, I found this pattern, I found that pattern, I found that pattern, but all other patterns didn't occur, for example. Then it would give a positive reward if those patterns occur and a negative reward or value if another pattern occur. And this is actually exactly the case for something which looks like a 0. It consists of this part over here, of this part over here, and kind of this part over here, and maybe this small area here is missing in these examples now here. But if I combine those patterns, I get something which looks like a 0. So the further I go down in my network, the more patterns basically can get arranged, and the occurrence of this pattern is evaluated in order to generate the next signal. So if this pattern, there's for example one pattern which says if this is active, this is active, this is active, I will be switched on. And this is then the pattern or the neuron which gets switched on if this pattern appears in the image. So just as an illustration, we can see this. The first layer are the raw pixel intensities. The second layer are kind of very simple patterns, just combining pixel intensities. The third layer are kind of then combined simple patterns into more complex patterns. And the last layer basically takes a combination of the final patterns and turns them into digits. Of course, it doesn't have to be the case, and this should be explicitly said in here, is that this layer, those simple patterns, are individual patterns which actually have that shape or look like this. That's not said at all. It can be patterns that can be activated anywhere. There's no locality as those patterns show up over here. I'm taking the whole input image into account, so it could be that I'm also taking other pixels somewhere into account which should be activated. So this locality over here is just here for illustration purposes. It really generates those simple patterns and combines those simple patterns, so in the end that I get a good signal if it is a 0 or a 1. And what's also important to note is that this is something that is all encoded in the network. So the weights and the biases of the network encode this whole procedure. And this means compared to other classification systems, such as random forests, for example, or support vector machines, we typically don't need to define manual features over here because the feature computation is basically included in the network. It's included into the weights and biases so that no manual design of features is needed for this type of systems. I'm connecting the raw input pixels on the left-hand side, and I get the result out, and the feature computation is automatically done inside the network. That can be a great advantage, but can also be a disadvantage. The great advantage could be that I don't need to sit down as a user and need to think what features could be great and actually write that down. I can let the system, when I'm learning such a neural network, figure out on its own which features are relevant. On the other hand, I can't put any background knowledge into the system and saying, I know that's a good feature, please use that feature. And I may need to look into a lot of different examples of training data in order to learn features that actually do that task well. So there's a pro and con to this. But overall, there's actually quite advantages if you have a system which can learn the features as well. So then we can look into the classification performance. If I now put in images which look like this 5 over here, and I'm getting this result out, I say, great, that's good, that's what we want. If I, however, would have a different dimension here activated, let's say this would be activated and this would be deactivated, then this would be bad, this would be a mistake. So this would be a correct example, and having another output vector here would be a wrong example. And there's a standard, the MNIST data set, which consists of all those handwritten digits. And if you use a standard neural network like this MLP over here and perform this, train the network and run the classification, then you will get a classification accuracy of about 96%. That means 96% of those handwritten digits are correctly classified. And that may sound okay, but not too great. But if you look to the database, you actually see that there are some tricky examples out there. Just put some of them which are kind of not that easy to actually identify. So with this one, even probably more people would have issues, or the question, is this a 0, is this a 6? Something which can also be seen as quite tricky. You can improve the network and build better models, not just these very simple models that I've shown here, but more complex one. And then you can actually bump up the accuracy to something around 99%. That's a result that you get with those models over here. So the question is now, how do we actually get such a network? I only explained so far how a network works given those weights and biases. And I think it became clear that those weights and biases basically find what pattern the network is actually looking for. So the question is, how to actually design a neural network to actually solve this task? How to set up an MLP to solve exactly this problem? On one hand side, the structure of the network has an impact. So what's the topology? What are those connections? How many hidden layers? What's the size of the hidden layers? What is the size of the input layer? What's the output layer? Which activation function should I use? This is basically something which tells you, which has an impact on what the network does, but also the parameters that I put in there. What are the weights? What are the biases? And how to set them? That's kind of a key question over here. And that's a question that we're covering in the second part of this lecture. And this is something which is referred to often as learning this neural network. And we do so not by manually sitting down and filling all those parameters here with values, but with showing the system positive examples of what it should do. So we provide 10,000 images of ones and say these are all ones, and 10,000 images of twos saying these are all twos, and so on and so forth. And then let the system figure out on its own how to set those weights and biases so that it performs best under that task, under that data set that we are actually providing. And this is what we refer to as learning a neural network, and something that we will look into the next lecture. So in this first part of the lecture, I introduced what neural networks are, at least very basic neural networks, so-called MLPs. We didn't look into other networks, except of saying that they exist and that their structure is different, maybe having different activations functions, having different individual neurons which have different properties. But what you also have understood, at least should have understood, at least from the MLPs, what's an activation, what's the weight, and what's the bias, and what the effect of these biases, weights, and activations, activation functions, or an activation itself actually are. You should also have seen that those networks typically have a large number of parameters. We haven't put that down explicitly, but you've seen that there are a lot of weights and biases for specifying a network. So the network that we have shown over here is around 100,000 or even more than 100,000 different parameters. So there's a large number of parameters that I need to specify. But once I have the parameters, it's actually not that much that a bunch of matrices and vectors that I need to multiply and add up and in order to do all the computations. And so linear algebra libraries are your friend in this context over here. And then we have shown how the MLP can be used for simple image classification tasks for recognizing handwritten digits, and also dived a little bit or inspected a little bit those different layers, what they are potentially doing or what the weights can be used for in order to generate local patterns of increasing complexity towards the output layer using those hidden layers. In the second part of the lecture, we will look actually into how to learn those parameters, at least on a basic level, indicate how we can have a way for actually finding a parameter set that hopefully does a good job in the outcoming classification task. I want to provide a few resources if you want to dive a little bit deeper. So a lot of the material here has been inspired by Grant Sanderson, great online educational resources on neural networks, which I really appreciate. And there's also an online book by Michael Nielsen, which take those examples and also code examples for exactly this neural network that I've shown over here are provided here on this GitHub page, so you can actually download them and play around with this network and also with more complex networks. And also a great resource is the Alpayalian Introduction to Machine Learning book, which also is a very easy to read book from my perspective. So with this, thank you very much, and I hope you got an idea what neural networks are, and you still don't know how to set them up, how to learn them, but something that we will explore very soon. Thank you very much for your attention.